Hey guys, this actually this example relate to the information we just discussed. So when Manchester upload it, you will see to it that it goes hand in hand. It means there's gonna be two videos. Just look at them, guys. Subscribe, share the videos. Hey, we are hoping to get 1,000, but I'm gonna tell you what, we would rather have 300 effective users of our channel than having 10,000 of people who are not using the video and they have just subscribed for the sake of subscribing. So please, man, subscribe, check the video, leave the comment, find the example or a problem, send it. We will look at together. I'm only the face of this. There are actually 5 of us. 3 of them are engineers. So please, whatever you think maybe it would help, bring it on, leave the comment. If you've got my numbers, you know how to find me. We are helping. We are not trying to be professional here. We share information, we grow. That's why this channel is Think and Grow. Let's discuss and grow together. Now, a reinforced concrete beam, 160 millimeter wide, must withstand a moment of resistance. It's just a nice terminology. You have done beams. It is actually moment. You have always taken moment about this, moment about that. The moment of resistance, the movement that beam must withstand. Like for instance, here we are on a seismically active environment here in Northwest, Rustenburg, Mpumalanga, Joburg. It's mines area. So for every depth there is seismicity. So that movement, it has to be withstand by the support, or supports rather. So this is moment, actually the moment of resistance. It's 70 kilonewton meter. There it goes. You can even see the unit is moment. The allowable stresses in the steel and concrete is 140 megapascals and 5.2 megapascals respectively, and the modular ratio M is given as 15. Always it will be 15. Calculate the dimensions D, N, big D, LA, the distance between the two forces, LA, all those is dimensions for the dimensions for the beam, and the number of 20 millimeter round steel bars that must be used, and the cover for the steel at the bottom of the beam is 25 millimeters. Is 25 millimeters. There is one other point maybe that I failed to mention, but I haven't failed because here I am, I'm mentioning it. For you to say this is an economical beam, or for you to say this is an uneconomical beam, there are conditions that must be met. Just like if when you are to calculate to connect transformers in parallel, you know there are some certain 5 or 6 conditions that you must be met. On this one, the conditions is that the area of the steel, the area, you know, an economical beam is a beam where the stresses meet their maximum value simultaneously. And then how do you notice it? The area of the steel is unknown, as well as the area of the concrete. It means both areas of concrete and steel are unknown. Whereas in an economical beam, how do you see it? One of the area is given. They will tell you the area of the steel is so much, or the area of the concrete is so much, where is B multiplied by N and so on. So basically this is the case. Now, as you could see, we are only given 20 millimeter round steel bars. We have given an area of 1 steel bar. This is not the area of the steel per se. Both area unknown. So for that reason, this is an economical beam. That's the most very important. You are only given a statement. From that statement, you have to deduce as to whether this is an economical beam or an economical beam. If on both occasions, steel and concrete, the area is not given, that is an economical beam. That is an economical beam. Now, the fact that also the position of the neutral axis is not given, we have to calculate the equations for design factors. That is N in terms of D, and LA, the distance between the forces, in terms of D as well. And it's equals to what? It's equals to, let's say how should I start it, Mr. Chester? Let me start it this way first. Let me check the easiest way to start it. I didn't want to use the formula. Or let's use the formula first. Let's say we said stress in the steel over stress in the concrete is equals to the modular ratio over the distance from the center of the steel up to the neutral axis divided by N, the distance from the top up to the line of the neutral axis. But you are told that this is 140 over 5.2. I'm not gonna put megapascals because it's a ratio, they're gonna cancel out. It's equals to what? This one is given as 15 D minus N over N. Now let's see, Mr. Chester. We say 140 divided by 5.2 is equals to 26.923. Let's cross multiply already. Multiply by N. This is equals to what? Is equals to 15 D minus N. Now we can divide by 15 here. 26.923 divided by 15. We're gonna have 1.795 N is equals to D minus N. Let's take this N this side. We're gonna have what? Let's say 2.795 N is equals to D. Let's divide by this. We will have to calculate N in terms of D, which is N is equals to 1 over 2.795 D is equals to what? 1 divided by 2.795, and it's equals to 0.35778. Let's make it 8D. So this is equation 1, N. This is equation 1, N. But remember as well, this, we say the centroid of a triangle is N over 3. Is N over 3. So the distance from here to there, this distance is LA. So LA is equals to D minus N over 3. We proved that initially. So this is D minus, this is calculated as 0.358 D over 3, and it is equals to what? It's equals to, or let's say D minus 0.358 divided by 3. It is 0.1193 D. So 1 minus 0.1193 is equals to what? This is 0.8807 D. That is equation 2. So this is LA, or lever arm, the lever arm LA. This and this are so-called design factors. Now, Mr. Chester, I can delete them. I can delete them. Right. I can delete them. Then what? Let's check. You know what I want to do first? Let me first prove that there's something I missed. There's an information, guys, I didn't mention in that information, in the previous information. So look, we know from the basics. Can I delete here, Mr. Chester? This for now. From the basics, we know that what? We know that force is equals to stress multiplied by area. And from this, if we said this is our point of neutral axis, we said this is breadth from the information, and the distance from there to there, we said it's n. And then this stress, because on the upper part, it is the stress of concrete. So this is the stress of concrete multiplied by, what is the area of this triangle? The area of a triangle is half base times height from sub A. Right, it's half the base times the height, the distance from there to there, which is n, is this. This is the force in the concrete. There is the force in the concrete. That's the point I wanted to show you first before I can continue there. Now, the moment of resistance, which is the moment of resistance in concrete is equals to the moment of resistance in the steel. We proved it as well. Now, let's consider the moment of concrete. Here, remember this. I wanted to show you first. Right. The moment of concrete is equals to 0.5 multiplied by the stress in the concrete, Bn. It's something like this, Mr. Chester. Yeah, it should be like that. And then this is given as 70. It is 70 multiplied by 10 to the 3 is equals to what? Is equals to 0.5 multiplied by the stress in the concrete is given as 5.2 multiplied by 10 to the power 6 multiplied by this is given as what? I think 16. 1 multiplied by 0.16 meters. This multiplied by n. N is how much? It is 0.358 d multiplied by now remember, this is moment is equals to force by distance. Still remember that from S1, I think, or standard 2, right? Meaning here we have to put LA there, force by distance. What is distance? It is 0.8807 d there, d. And it's equal to what? Let's check. It is 0.5 multiplied by 5.2 exponent 6 multiplied by 0.16 multiplied by 0.358 multiplied by 0.8807. Answer is equal to what? It's 131. It is 131,160,8896 d squared. This is d multiplied by d is d squared. 70 multiplied by 10 to the power 3. Now let's divide by this to get d squared, subject of the formula, and then we take the square root to find d. But for time, I'm just gonna say d is equals to, let's see, 70 exponent 3 divided by 131,160,8896 is equals to what? This much, and then a second function square root of that answer. It is equals to 0.7305 meters, which is the same as what? We multiply by 1,000 to convert it to millimeters. It's 730,54 millimeters. Why we convert it this way? Normally we don't like zeros in engineering. This is the effective depth of that particular reinforced concrete beam. And then what? If we've got that, it should stand to reason that okay, this n was this. N is equal to 0.358 d. But we just found d. What is d? 0.358 multiplied by 0.7305. And it's equal to what? 0.358 multiplied by 0.7305 is equals to 0.261, say 5 meters, which is the same as what? If you multiply by 1,000, it will be the same as 261,51 millimeters. This is the distance from the top of the beam up to the neutral. Now you've got the position. You have the position of the neutral axis. You have the position of the neutral axis from the top up to that line. Which line? Where the stress in the steel or concrete is equal to the stress in the steel. All right. Now we've got this. Now then that we've got this, what we're gonna do? We have to calculate what? Let's calculate the big D. The big D. But I would have liked to draw. The beam so that you could see what's going on. Let's draw this beam, Chester. I would have liked to draw the beam because I can't see myself what I'm doing. At least those values are there in the calculations. I want. Just look how it looks like this. You know, the worst thing I hate in life is struggle. I've struggled a lot. This is struggle. We really have to find good equipment. Yeah, it's good. This is my class. They know. Yeah, it's fine. That was just right. Hey gentlemen, let's draw that. Hope you could see, ne? I hope you could see. Right. Let's say here is that section, and you were told is 160 millimeters. Okay, fine. And then let's draw, say for instance, this. Let's say, okay, let's draw this. This is the reinforced steel beams. Okay. There where this line crosses, it is our neutral axis. And then this, okay, let me do this. It's fine. This one is the stress diagram, and the distance from there, that distance there is LA. Remember, it is D minus N over 3. Now look, the distance from there to there, it's 261,51, meaning our neutral axis is this line. The position of our neutral axis is 261,51 from the top of the reinforced concrete beam. That distance there, from there up to there, which is D, is equal to what? Is equal to 730,54 millimeters. Now we have to find this distance, this. And obviously this distance should be bigger than that distance, which is equal to what? Let's check. D. It will be the distance from there to there, which is D. This one. The distance from there to there is D plus the distance, or the diameter of this is given, the diameter of the whole thing is given as what? I think 20 millimeters. 20. It's given as 20 millimeters. This whole thing. But look, the concrete already covered half. It already covered that part. So this, it will be 0.02 divided by 2. The diameter divided by 2. Just for this, to get this thing. This. The distance, the cover from the bottom to the center of the reinforced steel is dead. Plus what? Is that distance? Yes. Plus the distance from there to there is this distance. It is the diameter of the reinforced steel. Plus the distance from there to there is given as 0.025 meters. And that is our D. Our D was found to be how much? It was found to be 0.7305 plus 0.02 divided by 2. It's 0.01 plus 0.025. And it's equal to what? 0.7305 plus 0.01 plus 0.025 is equal to what? It's equal to 0.7655. If we convert it to millimeters, it's equal to what? It's equal to 765.5 millimeters. It is that distance. It should be bigger than that distance. What is that distance? It is 730, meaning the distance from there up to there, it's 765.5 millimeters. These are the dimensions. And I think we should stop that problem there. What else did they want? Mr. Chester, I don't know what's your time there, but it's a lot. It's It's a lot. Or I also have to find LA, the dimension LA. LA, the distance, the lever arm from there to there, which is 0.70305 minus n over 3. How much is n? N is, what is n, Mr. Chester? I can't find n. Okay, n is there. Let's say it is 0.26151 divided by 3. That's L. It is 0.70305 minus, open brackets, 0.26151 divided by 3, closing brackets. Answer is equals to what? 0.615. 0.6159 multiply by 1,000 is equals to how much? 615.88 millimeters. Yeah, basically that's the case. Mr. Chester, I think we will continue with this next time. Yeah, but basically I was just showing you guys how to calculate the dimension of an economical beam, how to identify an economical beam if both areas are not given as an economical beam. If both areas are given, of one of the areas is given, then it is an economical beam. And an economical beam is used to where if you over design for normally worst environmental conditions. Let's say, for instance, in Durban there are normally strong winds, say maybe thunderstorms and so on. That's when you use an economical beam. You don't just design for the purpose of designing this. But we're gonna do that next time. This problem, I don't think it's over, but yeah, it's over, I think. No, it's over. Oh, okay. We are supposed to calculate the number of reinforced steel bars, but we will finish it next time. This video is too long, guys, but thank you very much. We have done almost everything and so on. Thank you. See you in the next video, hopefully for in future. Mwah. Shapra.